In snowy landscape, weather masked advancing darkness as wind persisted, revealing central problem of heat loss and shelter necessity, before stillness enclosed listeners within Viking Scandinavia. Wind exposure forced structures to prioritize enclosure before domestic function, ensuring survival against storms, reducing infiltration, stabilizing interiors, and delaying comfort considerations until safety thresholds met. That enclosure reduced airflow but trapped smoke, introducing ventilation problems that complicated heating, visibility, respiration, and long-term material durability within confined winter shelters during prolonged occupancy. Ventilation needs conflicted with heat retention, shaping roof geometry decisions as builders balanced exhaust paths, snow shedding, and airflow control under extreme cold pressures, environments seasonally. Roof geometry increased surface area, demanding insulation against conductive losses, where expanded exposure accelerated heat transfer through materials under wind-driven temperature gradients common in winter climates. Insulation requirements redirected material selection toward turf, timber, and earth, which offered thickness, trapped air, availability, and workable thermal performance, without specialized processing during seasonal construction. These materials added mass, slowing temperature change through thermal inertia, and buffering interiors from rapid external fluctuations caused by nightfall, wind shifts, and storms outside daily. Thermal inertia stabilized interiors, but required sustained heat sources inside to offset inevitable losses and maintain livable temperatures throughout prolonged winter occupation periods without interruption overnight. Sustained heat depended on fuel availability, constraining household energy budgets and forcing careful allocation of wood, dung, or peat across daily survival tasks in harsh winters. Limited fuel encouraged shared fires, centralizing hearth placement within dwellings to reduce redundancy, maximize heat distribution, and coordinate cooking, light, and warmth for all occupants collectively. Central hearths reorganized interior space, affecting movement, labor, and sleep as activities clustered around heat sources, reshaping daily patterns and nighttime arrangements within confined winter shelters. This reorganization compressed living areas, reducing air volume to heat and improving thermal efficiency by minimizing the cubic space requiring constant warming during cold season months. Reduced volume improved efficiency, but intensified moisture and condensation issues, as breathing, cooking, and snowmelt increased humidity within poorly ventilated enclosed interiors over extended winter stays. Moisture accumulation threatened materials, requiring raised platforms and drainage solutions to prevent rot, mold, and structural weakening caused by persistent dampness beneath living surfaces indoors continually. Raised platforms separated bodies from cold ground conduction losses below, reducing heat transfer into frozen earth and improving sleeping comfort during long nights in winter camps. Ground separation preserved body heat, yet limited usable floor area, forcing compact layouts and restricting storage, movement, and task separation indoors under crowded seasonal living conditions. Limited floor area concentrated occupants, increasing shared metabolic warmth output as clustered bodies collectively raised ambient temperatures through respiration and activity within enclosed winter dwellings daily. Concentrated bodies raised temperatures, but accelerated oxygen depletion rates indoors, increasing suffocation risk and reinforcing the necessity of controlled air exchange despite severe cold outside conditions. Oxygen depletion reinforced ventilation trade-offs previously introduced by enclosure design, forcing continual compromise between breathable air supply and heat conservation. Inside winter shelters under extreme climates. Design responses narrowed smoke holes, controlling drafts without sealing interiors to regulate airflow, limit heat loss, and still release combustion byproducts upward through roofs slowly intentionally. Draft control moderated heat loss, but allowed persistent smoke exposure, creating chronic irritation while maintaining survivable temperatures during continuous fire use across long winter nights indoors. Smoke exposure affected lungs, yet preserved timbers through antimicrobial effects, inhibiting insects, fungi, and decay organisms that weakened untreated wooden structures over extended seasonal occupation periods. Timber preservation extended structural lifespan, reducing rebuilding frequency over seasons and lowering material demands, energy expenditure, and risk during construction in short favorable weather windows annually. Reduced rebuilding conserved labor, critical during short construction windows annually when survival tasks competed for time, strength, and available community workforce under harsh seasonal constraints persistently. Short windows dictated modular building methods using repeatable components consistently, allowing rapid assembly, repair, and disassembly without redesign each season as conditions shifted unpredictably year two. Modularity simplified repairs, accommodating settlement shifts and resource variability locally, while preserving familiar construction knowledge transferable across landscapes and generations, without retraining builders during migrations frequently. Resource variability favored locally sourced materials with predictable performance characteristics, tested repeatedly under known climates. Loads, moisture, and temperature extremes encountered each winter season historically consistently. Predictable performance mattered because failure meant heat loss escalation rapidly, which could not be offset quickly with limited fuel reserves during storms, injury, or supply shortages. Escalating heat loss stressed fuel stores and human endurance simultaneously, pushing survival systems toward collapse under prolonged cold exposure, when recovery options were minimal, slow, or endurance limits shaped daily routines around fire maintenance cycles continuously, prioritizing feeding, tending, and protection of hearths over other activities throughout daylight hours and nighttime vigilance. Maintenance cycles restricted activity radius, reinforcing indoor-centered livelihoods during winters, as distance from heat sources increased risk and energy expenditure beyond shelter boundaries in severe cold. Indoor focus increased wear, demanding durable surfaces and finishes inside capable of withstanding traffic, tools, moisture, and constant occupation by families, animals, and shared winter use. Durable surfaces often used packed earth, balancing comfort and repairability with local materials that could be reworked easily when damaged through daily living, spills, and wear. Packed earth floors absorbed spills, but cooled feet through conduction, requiring bedding, footwear, and constant movement to maintain body warmth during prolonged indoor winter confinement periods. Cold feet prompted footwear and bedding innovations within confined spaces, where insulation layering materials, positioning, and shared heat management evolved to protect circulation during prolonged winters.
We will need more wood.
Bedding placement exploited vertical stratification of warmer air near ceilings, allowing sleepers to occupy elevated platforms, capturing retained heat rising above hearths while minimizing fuel consumption. Vertical gradients were limited by low ceilings, conserving heat overall while reducing air volume, slowing circulation gradients, and prioritizing retention over comfort variation within occupied interiors. Low ceilings reduced volume, but constrained smoke dispersal upward movement, forcing smoke to linger longer within breathing zones, increasing irritation while maintaining survivable warmth levels indoors. Constrained dispersal justified longhouse lengthwise layouts, aiding airflow distribution internally, as extended interiors allowed smoke and heat to migrate gradually along shared axes without sudden losses. Lengthwise layouts aligned entrances away from prevailing winds, outside pressures, reducing direct infiltration, gusts, snow, and cold air during entry events, common in exposed winter landscapes. Entrance placement minimized infiltration while permitting necessary access movements daily, balancing security, warmth, and routine circulation needs without compromising enclosure. Integrity during repeated use cycles throughout. Access movements introduced bursts of cold air during use events, briefly collapsing thermal gradients near doorways, forcing fires and bodies to reheat interiors repeatedly afterward again. These bursts encouraged vestibules or offset doorways as buffers, thermally creating intermediary zones that absorbed cold shocks before reaching living spaces during frequent winter entries exits. Thermal buffers slowed exchange, protecting interior temperatures consistently through storms by lengthening pathways for air, mixing, reducing pressure differentials, and stabilizing hearth-driven heat fields indoors continuously. Storm protection mattered because longhouses housed people and animals, together amplifying stakes, as livestock warmth aided survival, but loss threatened food transport labor and future mobility. Cohabitation added heat, but introduced hygiene and space conflicts, persistently requiring compromise between warmth, efficiency, waste, management, disease, risk, and limited movement under prolonged winter confinement. Managing conflicts required spatial zoning along the longhouse length axis, separating animals' work storage and sleeping areas, sequentially to control odor waste noise and access flows. Zoning separated functions while preserving shared heat distribution efficiently. Inside by maintaining continuous roof lines and airflow paths, allowing warmth to travel despite functional boundaries imposed intentionally. Efficient distribution relied on predictable airflow paths created by structure, guiding smoke heat and fresh air movements consistently without reliance on constant human adjustment or intervention. Structural predictability simplified daily behavior and reduced error likelihood indoors, as occupants learned stable patterns minimizing mistakes during fatigue, darkness, illness, or stress common in winter. Reduced errors mattered because small mistakes amplified winter risk, severely turning minor lapses into cascading failures, involving heat loss, injury, fuel waste, or fatal exposure quickly. Winter risk amplified because recovery options vanished once temperatures dropped below survivable thresholds, where repair travel or rebuilding became impossible without shelter, warmth, and daylight remaining. This irreversibility favored preventative design rather than reactive heating measures, embedding safety margins into form materials, and layout before winter arrived rather than improvising during crises. Builders added excess thickness to walls, accepting material inefficiency deliberately to create insulation reserves against settling rot, wind erosion, and unseen gaps forming over years silently. Redundant layers compensated for rot, settling, and weathering over years, ensuring structures retained performance despite decay, cycles, moisture, stress, insect damage, and repeated seasonal freeze-thaw. Long winters forced designs to perform continuously without maintenance interruptions, since repairs exposed interiors to cold risk and labor shortages during periods of darkness, storms, scarcity. Short summers constrained building schedules, increasing importance of proven layouts that could be executed quickly with confidence using familiar steps before weather shifted and daylight shortened. Proven layouts persisted, discouraging experimentation that risked winter failure by prioritizing reliability over innovation when mistakes carried fatal consequences under cold exposure, isolation, hunger, darkness, pressure. Design conservatism embedded architectural knowledge within tradition and inheritance systems, ensuring continuity across generations, as successful forms were copied, taught, remembered, and socially reinforced through survival. Builders learned by observing outcomes across winters, rather than instruction gaining trust in designs that endured storms, cold, and time, rather than theories detached from reality. Survival itself acted as feedback, reinforcing successful structural decisions repeatedly as failures disappeared from practice, while enduring forms persisted through continued occupation, seasonal return, and replication. Cold functioned as selection pressure, eliminating ineffective building practices without mercy, as collapse, heat loss, or death removed flawed designs from cultural memory entirely over time. Similar pressures produced convergent designs across Scandinavia and North Atlantic, regions where cold wind and fuel scarcity imposed identical constraints, regardless of language belief or lineage. Convergence produced standardized proportions, optimized for heat retention. Physics, balancing width, height, roof pitch, and volume to minimize loss, while maintaining livable space inside winter shelters. Width mattered thermally, while length scaled socially without energy penalty, because added length shared heat along continuous roofs without increasing exposed surface area significantly overall thermally. Narrow widths minimized exterior surface area relative to enclosed volume-reducing heat transfer pathways through walls, roofs, and ground interfaces during extreme cold exposure periods seasonally. Reduced surface area directly reduced conductive and convective heat loss, anchoring survival outcomes in geometry, physics, and material limits, rather than comfort preference aesthetics or choice. Fire warmth only traveled limited distances, reinforcing narrow interiors where proximity to hearths determined comfort zones, and spatial planning under persistent winter cold conditions, overall survival. Stone hearths radiated outward evenly across compressed interior spaces, allowing predictable warmth distribution that supported clustered living arrangements and minimized wasted heat within enclosed shelters daily. Stored heat mattered most during night when activity ceased. Fires burned lower, and survival depended on retained warmth, accumulated throughout daylight hours and communal labor cycles. Sleep reduced metabolism, increasing reliance on stored and shared warmth, making nighttime the most thermally vulnerable period within winter shelters, despite careful daytime heat management practices. Sleeping arrangements clustered bodies to reduce exposed surface area, maximizing shared heat retention, and minimizing losses during prolonged immobility under cold nighttime conditions inside winter shelters. Proximity transferred heat between bodies instead of losing it, turning social closeness into a thermal strategy rather than a cultural preference during winter confinement periods indoors. Close quarters normalized intimacy as functional necessity, not preference, reshaping social boundaries under survival pressure, where space efficiency outweighed personal distance norms during harsh winter living. Smoke exposure accepted because alternatives meant rapid heat depletion, forcing occupants to tolerate irritation rather than risk lethal cold through excessive ventilation or chimney drafts indoors. Health costs accumulated slowly, outweighed by immediate survival needs, as chronic irritation and lung damage were secondary to maintaining livable temperatures through winter storms indoors continuously. Chimneys would increase draft, accelerating heat loss catastrophically, making their absence a deliberate choice to preserve warmth despite smoke accumulation inside dwellings during extreme winter occupation. Air movement relied on buoyancy, differences rather than forced ventilation, allowing warm air to rise naturally while limiting cold air intrusion under sealed winter conditions indoors. Builders exploited rising hot air without formal theoretical understanding, using observation and repetition to shape openings, ceilings, and airflow paths effectively across many winters of practice. Ceiling height balanced smoke storage against livable breathing zone, preventing suffocation while retaining heat within reachable zones of daily activity for occupants during long winter seasons. Interior organized vertically by temperature layers, not uniform comfort, teaching occupants to adapt behavior spatially rather than altering structure dynamically under persistent winter cold stress conditions. Daily behavior aligned with warm zones, avoiding cold-prone areas, and reinforcing habitual patterns shaped directly by thermal gradients inside winter shelters during prolonged seasonal cold periods. Architecture assumed clothing. Insulation supplemented structural heat retention, treating garments as an extension of the building's thermal system during extreme cold, when fuel supplies were limited. Indoor temperatures expected wool and fur to complete thermal envelope, acknowledging that structures alone could not provide sufficient insulation in extreme cold during winter survival periods. Failure in clothing stressed architecture beyond intended limits, increasing fuel demand and exposing weaknesses otherwise compensated by layered personal insulation during prolonged winter storms and shortages. System interdependence meant small failures cascaded rapidly under cold, where torn garments, drafts, or dampness could overwhelm survival margins quickly during harsh winter nights indoors together. Routine repairs prevented minor leaks from becoming fatal exposures, making maintenance a daily survival task rather than occasional upkeep during extended winter occupation of cold regions. Cracks, gaps, and drafts demanded constant vigilance during storms, as unnoticed weaknesses could rapidly drain heat and endanger occupants inside enclosed winter shelters overnight repeatedly endured. Each winter tested design assumptions without forgiveness for errors, enforcing strict selection on forms that failed to meet environmental demands under cold wind darkness. Scarcity conditions. Surviving houses proved systems effective through repeated seasonal endurance, validating design logic through continued occupation rather than written records preserved by use memory, tradition, and necessity. Excavated remains reflect what worked, not failed experiments, biasing archaeological records toward successful solutions filtered by survival pressures over centuries of harsh winter environmental testing repeatedly. What survives represents optimized solutions filtered by environmental pressure, requiring careful interpretation rather than assuming completeness of past experimentation across different cultures, regions, climates, eras studied. The structure functioned as integrated thermal, social, and biological system, coordinating heat bodies, animals, and routines into one survival mechanism during prolonged winter habitation cycles continuously. Longhouses prioritized function over symbolism or aesthetic expression, shaped by necessity rather than display within harsh winter environments, where survival demands dictated every architectural decision made. Every dimension reflected constraint rather than stylistic choice, encoding physics fuel limits and labor realities directly into built form, shaped by winter survival pressures over generations. Extended darkness increased indoor reliance, amplifying design importance as shelter became primary world during long winter months, when outdoor movement risked exposure, injury, disorientation, death rapidly. Fire provided illumination, further centralizing hearth necessity as light, warmth, and activity converged around a single core space within. Enclosed winter dwellings at night repeatedly occupied. Central light reduced accidents during confined winter activity, improving safety while reinforcing spatial organization around hearth-centered interiors, where tools, movement, cooking, and sleeping overlapped constantly indoors. Winter life contracted inward, reinforcing enclosure as survival logic, where movement minimized exposure and architecture replaced landscape as lived environment during extreme, cold, dark months annually. Longhouses embodied accumulated adaptation to cold, wind, darkness through generations of refinement under relentless environmental pressure, shaping reliable shelters for families, animals, labor storage, survival together. Together, these constraints produced a structure that simply worked, not elegant or symbolic, but reliable under conditions where failure meant death during unforgiving winter survival contexts.